In this video, we want to describe the theory behind the STEAMBOAT experiment. The experiment you find both here and in another video published few years ago and linked in the comments. In that video is taught how to build such a boat. Therefore, we won't repeat it here. The task of this presentation is to understand how the toy works instead, from both a mechanical and a thermodynamic approach. Since some measurements are difficult to obtain, we will skip them and do some assumptions with the purpose to focus on the principles rather than strive to represent a perfect model. Let's start. The first part of the video is the experiment. Then we do our measurements and observations. Soon after starts the theory. First the mechanical and then the thermodynamic analysis. At the end of the video we will comment if the theory is satisfactory and how we can improve the experiments after we understood its working principle. We refer to an existing video linked in the comment how to build a steamboat. Here we resume only its components very briefly to understand the experiment. The boat has a wooden frame, then a copper coil, a heat source that in this case is a wax candle, a protection shell made by an aluminium can, and 4 gum spacers. They are added to prevent the swerving of the boat so that the width of the boat matches with the width of the channel and it travels straight. The video is run at 1 times speed. No intentional advertisement is done here. Let's see what we can meter from the experiment. First of all, the speed of the boat, c. Then the copper coil geometry, its diameter and its total length. Moreover, we can meter the burning rate of the candle, that is the mass lost due to the combustion in the unit of time. What we cannot easily meter, we need to estimate. The combustion efficiency ηc of the boat and the drag force capital F. Our intention is to understand the working principles, the physical laws behind it, and determine the efficiency of the system. Here we deal with many efficiencies: the total efficiency, the thermodynamic, and the propulsion efficiency, since of the special application. The boat speed c we meter directly by assessing the time the boat needs to travel the channel. We find something like 0.1 meter per second. The internal diameter of the copper coil is 4 mm and its length 880 mm. The candle burning rate is the burnt mass divided by the burning time. We find 0.08 gram per minute. Moreover, we know the heat net value of the wax being 43.1 megajoule per kilogram. The combustion efficiency we estimate at 60%. The losses are due mainly to the radiation and the hot fumes. Under those assumptions, it is possible to estimate the thermal power of the candle, that is, the product between the heat net value, the burning rate and efficiency. We land to 34.5 watt. The drag force is not only due to the water resistance, but also the friction of the spacers to the sides of the channel. I could not measure it directly with my dynamometer because its range starts from 50 gram force. I assume a value below 50 gram, but not too much. Let's say 40 gram force. This assumption we cannot verify, however, and we keep it for educational purpose only. The working principle of the steamboat we can divide in 3 steps or 3 transformations. Inside the copper tube there are 3 regions, here represented with different colors or hatches. The steam occupies the inner region, represented in red, where there is also the heating source, the flame. The water occupies the remaining space in the tubes. One part of the water is steady, represented in green solid, and one part is exchanged with the ambient, represented in green hatchet or light green. In the transformation A, the steam gets heated and its pressure increases. Final pressure is high. In the transformation B, the steam in the coil expands and pushes part of the water away from the tubes. The pressure drops. In the transformation C, the steam condensates and the vacuum sucks water back into the tubes. The pressure is constant. Now we apply the mass conservation to the stream, considering they are 2 parallel ones. The mass of the water that is ejected out of the tubes is the same mass that is sucked back, but the velocities are different. The speed v1 is the ejection speed, and v2 is the sucking speed. We assume v1 greater than v2. Afterwards, we confirm that. The water mass is the product of the density, ρ, the cross-sectional area, capital A, the velocity, and the delta time, times 2 because we have 2 streams. For the mass conservation, we argue that v1 into delta t1 equals v2 into delta t2. Delta t1 is the time of the transformation B, while delta t2 is the time of the transformation C. We call v the equivalent velocity, written in bold, while delta t is the sum of delta t1, delta t2, and delta t3. Delta t3 is the time of the transformation A, where there is no velocity because the water is steady. The equation 1 says that the equivalent velocity is the product of v1 and delta t1 divided by delta t. The momentum conservation says that the resulting force, capital F times delta t, is the sum of capital F1 into delta t1 and capital F2 into delta t2. But since capital F2 is negative, we make a difference. The force capital F we define also by means of the speed v. And if we express as well capital F1 and capital F2 by means of the respective speeds v1 and v2, remembering the equivalences A and B written above, we find the expression number 2. This equation says that if v1 is greater than v2, as we have assumed in the beginning, a positive force is generated. We are not in the position to determine the single velocities v1 and v2 as well as the time frames delta t1, delta t2 and delta t3, but actually we do not need them. That's because we can meter capital F directly or estimate it, as this is the effect of the drag and all other frictions to the boat, while the equivalent velocity v we can calculate indirectly, and we will see it in the next slide. As the result of the study done, we can say that a water stream is ejected backwards and the force is pushing the boat onwards. Does not matter if the water stream is made of 2 different ones, one entering and one leaving the boat, and that the force is a combination of 2 forces, one pushing and one pulling the boat. The overall force we can express with this formula. In this slide we call the water mass flow with the subscript W to distinguish it from the mass flow of the steam we will encounter later. Since we know the force, or at least we assume to know it, this formula we use to find the speed. And the speed is 3.9 meter per second. The water mass flow is the ratio between the force and the speed, also 0.099 kg per second. The useful power is then the product of the force and the speed, therefore 0.039 watt. The total mechanical power is the sum of the useful power and the remaining power in the jet. The power left in the jet is the kinetic energy of the jet itself. The velocity to be used for the kinetic energy is the absolute velocity, sum of the draft and the relative speed. But because they have opposite direction, here appears a minus sign. Finally, we calculate the efficiencies of the system. The propulsion efficiency is, for definition, the ratio between the useful and the mechanical power, and turns into 5.1%. The thermodynamic efficiency is the ratio between the mechanical power and the input heat, capital Q, instead. This quantity is 2.25%. The global efficiency is the ratio between the useful power and the input heat, that we can calculate also as the product of the above efficiencies. The result says 0.11%. To understand better the process, we perform now a thermodynamic analysis. The transformations A, B and C are the same as mentioned at slide number 7. First, we declare our assumptions. Number 1, we deal only with saturated steam, no air trapped in the copper pipe. To make it feasible, we fill the coil in the beginning with water. The transformation A from 3 to 1 is isochoric, constant volume. The transformation B from 1 to 2 is adiabatic, ideal, also isentropic. The transformation C from 2 to 3 is isobaric. Constant pressure, and because we are in the region of the saturated steam, is also isothermal. The steam volume at state 1 we assume being 60% of the copper pipe, and therefore we can calculate its value. If this is not true, we can change this assumption later. The pressure at state number 1 is 179 kilopascal and the quality 100%. Also, this assumption we can change, but we remember that the steam quality is not relevant for our calculation, because even though we start from a different less value, the work and the heat calculated in the process does not change significantly. The assumption number 7 is that the pressure of the states 3 and 2 is 100 kilopascal, also atmospheric. We run now the calculation for a unit of mass using the program THERMONATOR that you can download from Google Play for Android users. The link I left in the video comments, but alternatively you can also use the steam tabs from SPIRAX SARCO or from other vendors. Also the link is in the video comments. From the tables we get the specific volume of the state 1, and we can now calculate the steam mass because we know the volume occupied by the steam, capital V1, as assumed at point number 5. From the steam mass, using the volume of the state 2 from the table, we can determine the volume of the steam, capital V2, at the end of the expansion. From the unit heat Q31, we can get the steam mass flow. The unit heat Q31 is given by the difference among the internal energy at states 3 and 1. We can find them in the steam table. The mass flow is the ratio between the heat power capital Q and the unit heat Q31 and turns into this value. From the mass flow and the mass calculated in the previous slide, we get the process time delta T. This value we can confirm experimentally by metering the frequency of the water strokes behind the tubes. The metering says 0.2 seconds. Also, we need to change our assumptions for the volume capital V1 guessed at 0.5 of previous slide. By taking 67% of copper pipe, the calculated delta time is now matching with the experimental one. Let's calculate now the work of the cycle, that is the sum of the work over 3 transformations, 1, 2, 2, 3 and 3, 1. We remember that delta U is the difference between the unit heat capital Q and the unit work capital L. For an adiabatic transformation, capital Q is 0 and the work is the difference of the internal energy with opposite sign. And we can calculate this value thanks to the steam tables. For the isobaric transformation, the work is the product between the pressure and the delta volume, and we can calculate also this value. For the isochoric transformation, the work is 0 because delta V is 0. And finally, we get for the unit work this result. Once calculated the work capital L, the power is the product of the work times the mass flow. We get 0.82 watt. This power must be equal to the one calculated at slide number 8. Actually, there is a slight difference. Therefore, we need to change the assumption number 6 at slide 9. By putting P1 equals 174.5 kilopascal, all other parameters will change. So we need to run the calculation again. We found new values for the mass and for the mass flow of steam and for the delta time. Since the delta time is not very different from the experimental value, we do not need to change the assumption for capital V1. And finally, we find that the mechanical power is matching with the one at slide number 8. It is also possible to display the graphic in the chart temperature entropy, so we observe the adiabatic transformation 1, 2 being isentropic. How to increase the thermodynamic efficiency? This efficiency is very low. We metered 2.25%, and the reason is due to the Carnot effect. In fact, if you calculate the efficiency of the Carnot cycle, which is the maximum efficiency across the temperatures of the cycle, we get 4.4%. And the maximum temperature in the process, that is 117 degrees, is also confirmed by experiment. In the thermocouple, the display temperature is less, is 111, because it meters the average one. We remember that the cycle is very quick, being the delta time just 0.2 seconds. To increase the temperature of the cycle, we should increase the pressure. And to do this, we need to increase the length of the pipe to have more pressure drop. Just to make an example, a theoretical one, if we would like to have a thermodynamic efficiency of 10%, the Carnot efficiency should be 19.2% and the temperature of the cycle should reach 188 degrees, also 12 bar, which of course is very difficult to achieve. How to increase the propulsion efficiency instead? The exhaust speed of the jet is actually too high, almost 4 meters per second, and to reduce it we should use a tapered pipe divergent. If we increase, for instance, the diameter of the pipe to 10 millimeters and the velocity of the jet drops to 1.6 meters per second, we get a propulsion efficiency of 13%. We remember that the propulsion efficiency we can express with this formula, where alpha is the ratio between the velocity of the jet and the velocity of the boat. And this efficiency has a maximum when the speed of the jet is equal to the speed of the boat. Afterwards, the efficiency decreases. And how to increase the combustion efficiency? We notice that this efficiency is not considered in the overall count. The heat is lost due to the radiation and the hot fumes. The solution could be to make the can insulated or improve the flame's distribution by using, for instance, a multiple candle, either 2 times or 4 times flame. As a conclusion, the steamboat is not a very efficient motor, however simple to build and nice to see. Further experimental trials can be done to countercheck above conclusions. The presentation is finished. I apologize for having not been able to run all the required measurements. As you have seen, we made many assumptions. Actually, we adopted a simplified model to describe both the mechanical and the thermodynamic behavior and understand the principles behind. Thanks to the study, we could get some hints how to improve the efficiency of the boat, or its speed, in other words. For lack of time, I could not repeat the experiment under changed conditions, but you are encouraged to do it and then let me know how the boat is performing. See you soon. Thank you for attendance. Bye bye.